Does anyone know how to type a tilde on a Danish keyboard? No.
Just do this. Wiring.
Not initially, but...
Thanks.
Since you stay inside this area,
Uh-huh.
like here, not go all the way here, because you get all the cables. So just like here, and up to the computer.
Up to the computer, but
Because you
nowhere.
get you on camera. And,
Okay, but I
you
can't
screen.
go over there.
No.
Okay.
Then I need to.
I'll just like point from here.
Yeah. And
Okay.
You have this laser pointer here.
Yeah, I'm sort of terrible with those,
Okay,
but I can try.
You can try. Just don't do it in our eye.
Oh, that's not so bad. It's like big or something.
Did you figure it out?
No, it's not gonna work.
Okay, sorry.
But that's okay. That's okay. I figured I would try it, and if it didn't work, it didn't work. So. I think all the clocks are a little fast.
I think you're right. But the PC agrees with my phone, so
Yeah, which agrees with my watch, which also agreed with my computer. So.
we'll call that the right phone.
Yeah. On the theory that if you say something enough times, then it becomes true.
That's right. So I toured NIST in Boulder, Colorado a few years ago.
Uh-huh.
And where they keep time. And I found out there's not one clock. It is some sort of statistical model that gets input from clocks in the U.S. and in Paris and someplace else. And so they derive the time from this model. So you can't point at the clock and say.
They derive time from time. It just keeps.
Yeah.
That's kind of cool, actually.
The other thing I found out is that there's one thing that mankind has built, an operational system that actually has to compensate for the distortion of space-time.
Uh-huh.
And it's the GPS systems, and they actually have to...
Oh yeah, the satellites are a little bit different. They're just enough outside the gravity well.
And they're just enough that they actually have to have a correction factor.
Excuse me, can I just move this to the other side?
Oh, sure.
Okay, thanks.
Okay, will that work? Okay.
Okay, we're going to wait one more minute for folks to make their way in. There's plenty of room in front in the first couple rows.
Isn't there always?
And there's power down here.
Bribery.
So just to make sure you're in the right place, this is monitoring at high speeds and within regulations, session 3B. We're going to hear from KATA, from Janet, and a little bit different kind of story from Internet 2 about what they're rolling out in their new network. I have some slides up here. Welcome. Please turn off the ringers on your cell phones and the volume on your laptops. That's much appreciated. Some reminders about the poster presentations this afternoon. The conference folks are very proud of the poster sessions this year, so I encourage you to take a look at the posters. And the boss this evening. Because there's not going to be food out here in the evening, the conference has arranged to bring in a hot dog stand. So if you're going to stay here for the BOFs and you've realized as the buses leave that, can you not hear me back there? Is that, I just have to, did you turn it, I've just got to hold it really close. Okay. So the BOFs tonight, if you're staying for the BOFs and your blood sugar is going to run too low, there's going to be a Danish hot dog cart out here, I think after 5 o'clock, and you have to pay for the hot dogs. They're not included in the fees, but I hear they're really good. So yes, so 5:30. I'm outside 303, which I think is this building. There'll be a hot dog stand for everyone staying for the BOFs. So I'm kind of curious, how many people are going to stay for the BOFs tonight? Raise your hand. So, handful. Okay. Okay, so if everybody's made their way in, I'm going to let Colleen from KATA start with her presentation. And what we're going to do is each of the presenters will present at the end of each presentation. We'll take questions. Since this is being webcast and recorded, raise your hand. We'll get the mic to you before you ask your question. And if it's this mic, you have to put your mouth really close to it. So thanks, and thanks, Colleen.
Thanks. So can everyone hear me? I guess is a good place to start. I'm Colleen Shannon, and I'm from KATA, and I'm here to kind of give an update and a general overview on our current KATA activities. So I think I'll start with who we are. So KATA is the Cooperative Association for Internet Data Analysis. It was started by Kay Claffey about a decade ago now, so we've been around forever in internet terms. And our goals include, our overall goal really is to measure and understand the global internet. So not so much like what's happening on our specific campus or one specific network, but just in general, what is traffic like, what are people doing, how are things working, that kind of stuff. And in order to do that, it turned out that we needed to do a lot of other sort of more fundamental things. So a big part of what we do is the development of tools for measuring and analyzing internet data and collecting it too. And also doing the actual collection and curation of internet data and trying to share that with other folks so that they have data to do research on. And then we end up doing some visualization based on the data that we collect and the research that we do. So those are basically the things I'm going to be talking about today. I'm going to talk about some of our current research areas. I'm going to talk about our data collection and what we have and how we're distributing it. And I'm going to give a brief overview of some of the tools we have. And I tend to talk pretty fast, which is bad enough when I'm talking to people who speak English natively. So if you need me to slow down, please wave your arms or interrupt me or something.
You're better than KC.
Yes, I am better than K, but that's not really a good metric by which to judge. So I'm going to start with some of our macroscopic topology measurement. And the folks that do this at KATA are Brad Heffaker and Young Hoon. So we've had this Skitter project that's been going for, I think, 9 years now, which is basically doing traceroute-like measurements to about 500,000 destinations around the internet from between 20 and 25 monitors over the history of the project. We currently have, I think, 22 active monitors, and we're working on bringing another 20 that we recently acquired up and running as well. So we use that data to do a lot of routing and topology research and also some visualization. So looking at things like how long are paths on the internet, how well does data like route views or peering data actually show where traffic is really going when you actually look at trace routes and the paths that things take, that kind of thing. And as a part of running this Skitter project for a very long time, we've decided that it's not Dedicated infrastructure is great, but we'd get a lot more use out of the boxes that we have deployed if we could share and be able to run more active measurements on them than just these traceroute-like measurements. So one of our new projects right now is the development of Archipelago, or ARC for short, which is a new sort of measurement infrastructure architecture that can coordinate measurements. So if we're doing our skitter measurements and doing trace routes to lots of places, if two different monitors know that they always have the same path to a destination, they can tell each other that and then only have one of them probe them. So we're doing less redundant probing. We want to get to shared use of the measurement infrastructure. So it's not just these 45 boxes that KATA uses to do this one specific task. We'd like to actually let other people be able to run active measurements from them. And in a shared way, and also in such a way that the measurements don't interfere with each other and corrupt the data that's being collected. So a big part of the development is also security measures to both ensure responsible use of the boxes and make sure that somebody can't take them over and use them to do something bad, and also to make sure that we have data integrity. So one person collecting data doesn't influence the results of another measurement that's going on at the same time. We also do a lot of work in routing, and Dima Krikov is the main person that we have working on these things. The big thing that he's done lately is realistic topology generation. So working on how you can generate graphs that preserve kind of the properties of the real internet when you're doing research. And he has this DK series that you can basically specify properties and then generate graphs that satisfy those properties. And they're guaranteed to always do that. And you can get more specific and add more properties, and they're guaranteed to still reflect all of the properties that you specified before. So if you try to incorporate a new thing, you don't break all of the things that you've already tried to incorporate into your model. We also have AS adjacency. So we've taken this traceroute-based data of how traffic goes through routers on the internet and actually abstracted that to the autonomous systems in the internet and how they're actually connected to each other. And it's different from the autonomous system graph that you get if you use like route views data or other sort of routing data. So we have these AS adjacencies, and we have that available to researchers that want to use it. We've also done some sort of classification and taxonomy of ASs. So how many customers do they have and how many providers? Can you infer that from the traceroute data that we have and other data like whois data that you can also get and combine that together? And that data is also publicly available. We do a lot of work looking at the DNS system. Dwayne Wessels and Marina Fomenkov are the main people that work in this area. So a lot of what we do are DNS surveys. We look for open resolvers, which are basically the DNS equivalent of open relays for mail. So basically, they're servers that will do recursive queries, but from anyone on the internet, not just people in their own local domain or the people that they're expecting to serve. And you might think that was a good thing. It's a great public service. It makes things work better. When I travel, I can still use my laptop. I don't have to change any of those DNS settings. But it turns out to be a problem because they can be used for denial of service attacks against root servers and other servers. And they're also a problem in cache poisoning, which is the next bullet, so I'll talk about that a bit. We also do surveys looking for cache poisoning, which is basically looking up an address or providing an incorrect referral to a DNS server that then caches it and passes that inappropriate referral on to someone else. So say I want to redirect everyone from an organization who's going to google.com to my own page that has malware that will infect them or just advertising that they can see or whatever. If I find an open resolver and I do a query and I tell it that I am authoritative for this name and I give it this record, then everyone in that organization that looks up google.com is going to be redirected somewhere else in a way that's transparent to the users. There's no way they know what's going on. They still have the little lock symbol in the corner of their web browser or whatever. So open resolvers are a problem because they're vulnerable to cache poisoning. But there's other ways to do cache poisoning as well. So we do surveys looking at how prevalent that is. And we look at the name server software prevalence. So of all of the DNS servers out there, how many of them are running Bind? How many are running DJB DNS? How many of them are running the Microsoft DNS server or other DNS servers? So that's one of the things we do in DNS. And then we also take traces at some of the root servers and do analysis of the query loads and how well the whole system is working, where the clients of those servers are located around the world, how they're distributed, that sort of thing. And we do some RTT measurements to these DNS servers and then GTLD servers to see how well they're working. So that's what we do for DNS. We also do some security work, which is mostly stuff that I do with David Moore. Recently, we did analysis of the sort of Nixum, Blackworm, Commissar, Trutro, My Wife. The thing had like 28 names. I'm kidding. I'm not kidding. All of the malware things these days seem to have, this long string of names. But basically that was a virus it was just an email virus, so it wouldn't have been that exciting. Deleted some files once a month, that kind of thing. Except that it phoned home to a website counter, and we were given the logs from this counter that we could use to analyze and see how it spread over time, which was really interesting. The other challenge there was that the URL that did the counter that all of the infected machines phoned home to was publicized, so it also received a lot of traffic from people just looking to see how many were infected. And it was a target of a bunch of denial of service attacks, so that all polluted the data and made it more of a challenge to figure out who was actually infected. We have a project called Spam Scatter, where we have some large feeds of spam traffic, and then we look in the spam traffic for URLs, and then see how long the servers that are actually serving, the scams or the phishing sites or the Viagra sites or whatever, how long they stay up compared to how long the spam is being sent, where they're being hosted, if they're moving around from machine to machine, that kind of stuff. We're working on botnet economics. So botnets are basically, they're one of the current, I think, biggest security threats. It's with one person and some software, you can look for and break into a large number of machines in a sort of semi-automated manner, and then use those machines to do denial of service attacks, to send spam, to do a lot of other things in a sort of a coordinated and controlled way. And so one of the things we're looking at is the actual, sort of the underground economy in trading these bots once computers has been infected, and how much they cost. Because one metric you could think of for security and attack mitigation efforts, how effective they're being, would be if the prices are going up, because the resource is becoming more of a scarce commodity. And unfortunately, as far as we can tell, that's not happening. We also have been doing some worm risk analysis. So the witty internet worm that spread a couple of years ago, we had a grad student that reverse engineered the random number generator for it. So combined with that and some data that we have on the spread of the worm, we can actually work backwards and see exactly who infected who for the whole course of the worm, pretty close. So that's a really interesting thing, because it lets us answer questions that haven't been able to be answered before, like if you get infected with a worm, what's your risk of infecting others? So far, all we've really been able to look at is what's your risk of getting infected yourself. But it gives you some idea of liability and also what the benefits of being a good citizen are. And finally, another thing we're working on right now is anomaly detection. So there's been a lot of work in the past, and it's mostly a solved problem, looking at large volumes of data and finding big things. So finding a denial of service attack and tracking how it works, or these internet worms that generate a huge amount of traffic in a relatively short period of time. But there hasn't been as much work in looking for sort of new or unique things. One of the applications of this is sort of if you're looking at the edge of a network and you're measuring traffic, you're going to see, let's say, the web servers on that network as they're serving data. If you're just looking at the traffic overall or sampling it, you'll see that a lot. You see most of the new packets that you see tell you, hey, you have a web server, hey, you have a mail server, that kind of thing. And really what you might want to know is, you might want to know some things about your web server and your mail server, that they still have about the same number of people as yesterday, that kind of thing. But you would also want to know sort of interesting and small obscure things like, oh, it looks like my CEO's desktop has just turned into an IRC server. I don't think it should be doing that. So looking at ways to sample for new or unique events that you don't already know about, while still also providing some reasonable information about the continuing and ongoing things so you can detect trends there. So that's kind of our security work. And finally, we have Commons, which is our PI, the person that started our group. It's her current project, which is cooperative measurement and modeling of open network systems. And basically, it's in response to sort of three main problems. One is an infrastructure financial crisis. At least in the US, people just do not make money moving packets around. So they're trying to sell a lot of other services on top of that, like backbone network providers. Or a lot of them have declared bankruptcy, and it ends up being the government sponsoring the fact that they can't make money moving packets around. There's also a data acquisition crisis. It's extremely difficult to collect network data for people to do research on in a non-sort of research network, but just on real backbone networks and real traffic where users are using applications. And finally, there's an emerging trend for communities and others, and small cities and other small organizations to provide free wireless connectivity to people. But they're having a hard time surviving because they have a hard time getting connectivity to the internet at large, paying for bandwidth, paying for infrastructure, that kind of thing. I mean, for places where Google isn't paying for it for them. And so one of the solutions to that is a cooperative national backbone that connects these networks and provides free peering to academic and government and other institutions. So it provides low-cost access for the community wireless networks. And it also, one of the criteria that's required for connecting to this network is that you're explicitly consenting for measurement activities, for your traffic to be measured and monitored. Not in ways that compromise individual privacy, but just in general, you know your traffic is going to be collected, it's going to be used by researchers, and it'll be used to make better network tools and a better network in the future. So changing gears a little bit to talk more about our data. Our KATA data sets fall into 3 basic categories. So we have freely available data that anyone can download and anyone can use. We have some data that's only for academic and nonprofit access or KATA sponsors. And the reason for that is it's very difficult to get funding for data collection and distribution. It's not considered research and it's not considered engineering. And there's just sort of the 2 places that you can get money as a research group to do work. So we ask that people that have resources sort of contribute back to the data collection efforts. So our freely available data sets include the AS and router adjacencies that I talked about before, some anonymized data on the co-read and witty worms, so no real IP addresses, AS relationships, so like if you're a customer of another AS, or you're just a peer with it, or it's your service provider, the rank of various autonomous systems, so based on their out degree, so which are the biggest, which are the smallest, you can group them together and treat that group as an entity. And then the AS taxonomy I talked about earlier. And then the nonprofit or sponsor use data is the actual raw traces from our topology work. We have OC48 speed peering point data, and we'll soon have OC192 peering point speed. We're in the process of deploying 4 new monitors there. We have denial of service backscatter measured with the UCSD network telescope. So 4 different data sets there. We actually have the 2007 data coming out, which is all of the year data are quarterly, week-long traces of denial of service attack backscatter. And they're coordinated in time, so you get about the same week every year, so you could do trend analysis if you want. We have witty worm data with the original IP addresses of the people that were infected. And we have some DNS root and GTLD RGT data, so measured from a number of points what the RGTs to these servers are. I'm going to go back. Another big data project that we have is the day in the life in the internet. And this is something we're just getting going. So we had the first sort of wide-scale one this year, January 9th and 10th. And we got 7 DNS participants, so a bunch of the root and open root server network folks to collect data for us. And we also had 5 network participants, so people just collecting traces on their data. And we had our UCSD network telescope going then as well. But if you'd like to join future day in the life of the internet efforts, please email us and get involved, because we would like to see if we could actually get a real day in the life of in the internet covering a large number of places. The motivation for this project actually comes from a review of the current state of sort of internet and network science done by people outside of network science, so some physicists and some earth scientists and some other folks. And their main bit of feedback was that a lot of the research that currently is going on is not really of much practical use, and that we don't really have much data to do work on, and that was the biggest problem. And so they challenged sort of the computer and the network research community to come up with a day in the life of the internet data set that people could actually do research on that would be more practically useful. Sorry. So the next challenge for us, once we have some of this data, is actually distributing it. And we found that if you look around, especially if you look at papers that are published in these areas, there actually is data available. I mean, it would be great to have more, and that's certainly an area that needs a lot of development. But it's also possible to make better use of the current sources of internet data that exist. So to do that, we decided that we would build this thing called the Internet Measurement Data Catalog. I'm going to talk, it's new and it's something that we've put a lot of resources in, so I'm going to talk about it for a bit here. It has three main goals. The first is to facilitate searching for and sharing of data among researchers. So we want to index as many types of data as possible, including data sets that are not publicly available, because the reality right now is that most data is not publicly available. And the ways that people go about getting access to data is cultivating personal relationships or just calling people up and talking to them about this great new thing they want to do with the data, that kind of thing. But you can't take that step and try to get to know someone and let them know what you'd like to do with their data if you don't know what data they have in the first place. So we want to have some record of what data exists, even if it's not freely accessible, so that if you really need it to do the research that you're doing, you know where to start as far as trying to work out some arrangement by which you can get access to it. For the same reasons that most data can't be publicly available for privacy and legal and proprietary and other concerns, DATCAT doesn't store any network data itself. It just stores metadata. So records about where the data is, some statistics about it, and how you go about getting access to it. Another goal of it is to enhance the documentation of data sets via a public annotation system. So it's a way that people can give feedback about data sets, and it also means that when researchers are actually collecting their data, they have some place to write down their real methodology and what they did and what the problems they experienced doing a data collection are. Because if you look at papers in our field right now, there's tons about the results and the motivation and everything else. And you'll see the methodology is like a paragraph where they said, we collected some data and here it is. But nothing about how they collected it, what problems they experienced, what their sources of error are, all the things that you would need for us to actually be doing real science here. And there's a reason for that, which is that papers have short page limits, and reviewers, the first thing that they suggest that you cut out if they want you to put more information in is the methodology section. So this provides an external and persistent place that you can put information about data. And it's a persistent reference that stays with the data, not the paper that's about the data too, which is also useful for things like, I don't know if you guys know about the AOL data set that was sort of released and then retracted and taken down, and now there's no mention of it anywhere because it was a huge legal problem for AOL. But we indexed it in DATCAT. So while we're not serving it, there's a place that people can actually cite and can go to just for the original README or information about that data set. So it's useful for that as well. And finally, we'd like to advance network science by promoting reproducible results. I reviewed a very large number of papers that say, I have developed this great new system for counting packets or doing whatever, and I know mine is better because I ran it on my data set and I get better numbers than that guy over there when he ran it on his data set. But the only way you could really realistically compare these two is running them on the same data set, and that just doesn't happen. So at least this provides a way people can document what data they're doing their research on, and for other people to try to get access to that data and reproduce their research if they want to, or build upon it too. So sort of in summary, DATCAT lets you find data for research and engineering, annotate data sets so you can share information with other people. You can cite data, and you can also contribute data. We're currently beta testing our contribution tools to allow other people contribute and index their own data in the catalog. So our current status, DATCAT became available for public viewing a year ago almost. And the contribution interface is currently open to beta testers. Okay, we have 76,000 data items, 6 terabytes of data, and 33 collections, which are basically whole data sets, or publications where people have indexed their data in the catalog. This is an example of what it looks like. We collaborate. I'm trying to finish up here, so we collaborate with some folks, and there's some more information things. And the slides are all online if you want to look at this. And finally, we have some tools. So we have Coral Reef, which does packet trace collection and analysis and includes a real-time traffic report generator. And we're about to do a new release that will also do sampling on high-speed links, so you can run it up to 10 gig or OC192 links. Scamper, which is the next generation tool to do our traceroute-like measurements. Netromet, which is another traffic measurement and traffic metering system. And DSC, which lets us do our DNS server collections. And we also have some visualization tools. And I have a couple more slides, so I'll show those. Otter is a layout, and it's a Java-based layout tool. So it lets us produce things like this map of the internet topology. You can find out more about that on our website. We have Walrus, which is a 3D hyperbolic viewer that lets you look at sort of the topologies of things. So this is all the people infected with the code red worm and where they were in the network. And the color is by the number of infections in each sort of /24 that's shown there. I was going to do a demo of Cuttlefish, but Cuttlefish is a tool that lets you plot data over time. And it has sort of the night and day pattern of the Earth going by, so you can actually see diurnal effects in your data. And it will build animations of that. So I wasn't able to get the demo working on this computer, but if you go to our website, it's there. And that's it. Do people have any questions?
So I'll get a question started here. In the U.S., there are efforts to both for NLR participants and for Internet 2 participants to peer with the commercial internet to get a peering service. Would KATA be interested in instrumenting those links?
Definitely.
Okay, so we should talk to you guys about that.
Yes, we would love to.
Okay.
More questions?
Does DATCAT participate in the PREDICT project? You know, there's a research project to catalog various data elements.
So KATA is one of the PREDICT. We're a data contributor and a hosting site for PREDICT. So all of the KATA data that's available via DATCAT and more, actually, is available via PREDICT. For folks that don't know, PREDICT is a sort of US government project to collect data sets that are particularly useful for security research and then distribute those to the community. And it provides like a vetting framework and an application process so that highly secure data sets can be distributed in a more limited fashion and other data sets can be distributed more widely. DATCAT, it's sort of complementary to PREDICT because to get access to the PREDICT catalog, you need to apply and be approved by your organization and a lot of things, whereas DATCAT is just freely available. But data that's available via PREDICT can be indexed in DATCAT if you want to publicize it further. So people know that basically in your data access, in the part about your data set where you list data access, you can just say, go to PREDICT and apply, and you can get access to it this way. So there's really complementary systems, but they work together quite well.
So while we're changing speakers here, I want to remind everyone that you, I think, should have an email about your evaluations. And well, I guess that's a good thing. Thank you very much.
Yeah, I'll just put it in my pocket. It's fine.
I'm a little slow. As I was saying, you should have an email about your evaluations, and I encourage you to be filling those out during the conference, not waiting till the end to do the conference. We just had a great presentation, and that should inspire you to fill out your evaluations. So Steve Williams is going to talk to us about Janet.
Cheers, thank you. I'm going to cover, I tend to walk around a bit, so I'm going to apologize to the camera guy. I'm going to cover something about what we've been doing in terms of monitoring. I really like the KATA work because it brings so much stuff together and all these data sets, and you can just get all these groovy pictures of things of the internet. I love it. What we're trying to do in the UK at the moment in terms of bringing all of these measurements together, we've had lots of things being measured over the past umpteen years, but they've tended to be on disparate systems, stored in different places, processed in different ways. And one of the problems that we have had in the research papers, exactly as just said, is that there is no consistency between data sets, between methodologies, and there just isn't the material available where people can go and say, I want to look at what Janet has been doing for the last year, go and get the data, apply consistent methodologies, and do this work. I'll give you an overview of why we're doing it, something about the legal requirements that we face in the UK, and at the moment there is a significant difference that we're seeing between the legal approaches in the UK and what some of the American researchers want to do, and that's creating a little bit of tension at the moment. That needs to be addressed. We just have to work our way through them. So when we had SuperJanet 4 running for quite a while, the new version, SuperJanet 5, is in place now and has been running since the end of last year. When the requirements analysis was done for that, we talked to a lot of researchers, to groups all over the place, and of course everybody tells you what they want and you throw it into a pot and try and pull something out. And I'll give you an overview of the structure of a network and how we're trying to address all these requirements in a moment. But we have, on the monitoring side, a definite and clear vision to say we want better visibility of the network. We can't see enough at the moment of how the network is performing. Please provide that to us. So we have what is the fifth objective in SuperJanet 5, which is visibility. And we're trying to address that through these programs. So the demands from researchers, from network operations centers, we have a core network and we have regional networks, each of which have their own network operations center. We have institution people, network managers there. They're all asking for similar but slightly different things, different perspective. Metrics from all of the layers, from flow data, from views into packet data, payloads itself, right down to is my optical link up or down. And all that whole range of data needs to be in one place, really. Routing information, packet capture data. I see that one of the questions we've had up until fairly recently is how are we going to deal with 40 gig packet capture? Can we deal with 40 gig packet capture? I see that Endace had a press release out just a few days ago saying that they have released a 40 gig box now. So we can split 40 gigs worth of traffic into 4 10 gig streams, take them into 10 gig collectors. So there is actually a way forward moving towards the 40 gig links. And flow data has been a big thing that's been becoming more and more important from the research perspective as well as from an operational perspective. The challenges that we have in all of the big networks in terms of this is just the sheer amount of data that we're getting from the flow capture. How do we deal with it? How do we deal with the samples? What sample rate is good enough to still get enough data that it's meaningful to researchers, to operationals, to search people, etc. And of course, when we start looking at packet and flow data, we start looking at the legal requirements. And there has been a huge change in this area in the last 5 years or so. And we now have criminal offences. It is not just that it's naughty to look at somebody's data, it's that it is criminal, and you can go to jail for it. And we have quite a hard time educating some of our computer science students that some of the things they maybe want to do is not really the done thing. It has made a big difference, and it's quite a bit of effort to deal with some of this. Ethical behavior comes up in terms of research projects. Even in some cases where you can do things, maybe you shouldn't be doing things, or you shouldn't be publishing data in certain ways, and there are limitations there as well. So the push really in the UK for the monitoring perspective is for research. This is why we are building this system, or this is where we're taking the requirements for the system. The reason we're doing it from the research side is because if we can satisfy the research guys, because when you ask the researchers, what data do you want? They just say everything. What time scale do you want it at? Oh, millisecond will do. You know, how much data can you cope with? Oh, terabytes, it's fine. If you can satisfy all those requirements, then actually all of the other things drop out of that. They're just a different user interface into that data. And those are much easier to do. Do it the other way around. Do 5-minute data, and your researcher wants 1 minute, 30 second, or 1 second data. You've got to revisit the whole thing. Issues that we have, standards in measurement. There are some standards out there for storing, delivering measurements. People have heard about PerfSonar, NMWG standards, schemas, etc. But there's very little consistency between how things are applied in terms of research, in terms of doing things. Can we take a standard approach across measurement types? Can we interchange data? Can we compare two measures? One of the things that I have not yet been able to find, and I'm sure there are some things out there somewhere, is say, what constitutes a good link? You talk to people about where's the threshold between where should I upgrade this link? Now, in the ISP world, there are papers on this, and it's looking at the 80% measurement range. If it's an 80% measurement, then you're probably looking at upgrading it. Some of the measures that we start looking at, you say, well, if you're looking at a link on a 5-minute average and it's above 30%, then you maybe want to start thinking already about upgrading it, especially with the growth curves that we see in education networks. Because in 6 months' time, that 30% is going to be 50%, and that's on a 5-minute average, and all of a sudden you're getting congestion in the network. I'd love to know what a good link is. So we're being pushed by research. So many people using the network. Janet has I should say something I meant to say this at the beginning. You see the logo at the top left, JA.net. Ukerna is changing its name. Come June, we will no longer be known as Ukerna, we'll be known as Janet UK. And JA.net is the new branding. Blame the marketing people, it's got nothing to do with us. So don't get confused between Ukerna and Janet and JA.net. We're all the same bunch of people doing sort of the same work. Our stated aim in terms of research is to support researchers, to support the research communities, whichever community that may be. E-health, particle physics is in the trial, CDF and Atlas, astronomy, high-performance computing, biology, you name it. You know, if we can provide additional resources or do something on the network that will assist these researchers, this is what we're aiming to do. Obviously, there are costs, there are balances, there are benefits to be realized, and we have to take a view of what's affordable, what can be done, etc. But the whole point of having a national research and education network is to do research at the end of the day, so we have to support that. We aim to assist network researchers by providing access to this data that we're gathering on the network, by providing them access where possible into the network itself, by allowing them to co-host equipment, if we can, close to the center of the network. There are lots of possible things we can do, and we're just trying to do that. But we need to balance operational versus research requirements. You know, we have 1,000 higher and further education colleges, umpteen thousand schools relying on Janet for their 50-minute school lecture. You know, if the lecturer walks into that classroom and they don't have internet access for this first 10 minutes, that's a big chunk of the lesson already gone. It is critical now that we provide this reliability across the network. There's no point in having a network you can do research on if you're not providing the reliability as well, because people will go elsewhere. And the legal versus research requirements. Researchers want to do everything. They want to get the payload of the packet and look through it and compare payloads and do this and have the source of IP address, the destination, and they basically know what every single one of you has been doing for the last year on the internet. That's not such a good idea, the legal people have said, and there are privacy issues, Human Rights Act, lots of things to be dealt with, so we have to do it somewhat carefully. In SuperJanet 4, we had UK Lite, which provided an architecture to give dedicated bandwidth to researchers working in certain areas. And there are a number of projects that we're using and trying to develop a vision of next generation networks as part of this. Masts on the left has been quite interesting because they've been looking at doing packet capture on aggregated SDH links. So where UK Lite provides links between 55 and a gigabit across the network for various projects, and they're actually wanted to look at a 10 gig aggregated pipe in that and take reformat things, take things out and all the rest of it. But it didn't turn out to be that simple, because the slight variation of SDH that was used between the NDIS boxes didn't understand it, so it didn't work. So when we start getting into some of this detail, there are problems. There are always problems with this. Research on networks, we have got all sorts of people across the country working on all sorts of things, ranging from packet burst, optical burst switching, to anything you like, really. We've got dark fiber network going in between 3 institutions just to give them fiber to allow them to do anything they want on it, because there is no way we can let that anywhere near the production network. It's not even something you want to run on a channel. It's low-level protocol work, and you need dark fiber for it. Means that if it's something separate, we probably don't have to monitor it. But these are the people who are pushing us to provide more and more data on the network. They're very active researchers. The grid people, EGE, all the rest of it, the LHC circuits from Rutherford Appleton to CERN, and the tier 1 to tier 2 circuits within the UK. And we have a project which is looking at specifically monitoring the tier 1 to tier 2 circuits called GridMon, and that's looking at sharing that data amongst the tier 2 sites and making sure the network's operating correctly. Jive data, various high bandwidth use. All of these people are coming and saying, we want to see the optical network, we want to see flows, we want to see everything that's going on. And this is what fed into the requirements for the Supergiant 5 network. So at a fiber level, the network looks something along the lines of that. You can see all the regional networks are small little dots, and the core nodes are the large blue boxes. And we basically have fibers. We have dual access into all of the regional networks. So we have the reliability, the resilience built in. Rob Evans, sitting in the back, will be talking about that in one of the security sessions. Which is great, and it looks relatively simple. But then when we start looking at the actual network, all of a sudden we start finding out there are 100-odd network elements in there. All of these can be monitored. So we can actually get a huge amount of data out of the network if we can get access to the boxes. We can get up-down information. There are some performance stats we can get. We can bring up circuits, put new things in place. There's a lot of flexibility. And again, this is all of the data that we're able to pull and put into a system. And the challenge is taking this from all the way from the optical level all the way through to the flow level and building something that will enable us to do research on. So starting slightly further up, what are we doing in terms of monitoring? We've had a development project running for quite a while. We're throwing out the existing NetSite system that we have and replacing it with something that is going to be far more flexible and able to be developed into new modules, add new modules as we require different things for different services. For the basic sort of model monitoring, which we have to do against all of the end sites, we have things like Cisco IP SLA, the usual pings, SMB polling of interfaces, bunch of Perl scripts holding things together, and a big fat database sitting in the center of it. And that's the key to it all. And it gives us the usual things. This is the one thing that maybe we're saying, this is looking at service monitoring as well as just network monitoring. So we're looking at things running on the network. We're looking at how web servers are running. We're looking at how the DNS response time is performing, especially where you, Kerner, I was going to say, or Janet, whoever we are providing services to the community. How quickly do the email services respond? How well does our NTP servers work? How accurate are they? And it allows us just to give one view. You can look at a bunch of stuff and say, hey, those are red. That's probably bad. We should probably go and do something about it. One of those shows 75% utilization. It's probably something we need to do something about. This is actually from January, and you'll see it goes quiet about 4 o'clock in the morning, and then the yellow and then the black kicks in. And that's up to about 68% at peak on one of those links. Rob showed me some figures earlier that showed that link had actually reached about 90%, so that was great. But all these, this general monitoring is just pointing us to say, this is how the network is performing. These are the things you need to do something about. In terms of these links specifically, from London SCR4 and London SCR3, the two in the middle, we're putting in dual 10 gig links now. There'll be links from those two boxes up to Warrington SBR and Leeds SBR up on the top left and right to get away from this congestion. So we're sharing the load across these because obviously we can't keep running links at that. Between London SCR4 and London as well, this is Telehouse to London to our core POP. There's a 40 gig link which is almost in place. We've got the Sienna boxes in place, the lights have been turned on, and the routers are going in this week. We're hoping within the next few weeks to actually be able to run 40 gig traffic across that link. And this is where the concerns about being able to monitor 40 gig traffic comes in. So if we're going to start deploying these links and we have no means of monitoring them, and we have Juniper boxes in the network, now Juniper T640s are really, really bad at sampling flow data. On the GSRs that we have, we run 10-to-1 samples. On the London T640, we, a little while back, had to drop it from 1,000-to-1 to 2,000-to-1 sampling rate because it was getting too busy. There are picks that can be added, there are things we can do, but at the moment it doesn't look like we can get anywhere near the 10-to-1 sort of sample rate on these. And that means we have problems in getting visibility for CERT, for other security and operational matters into that. If we can do 40 gig packet capture, we throw all those problems away because we've actually got much better facility there that we can do all these things on. Flow data, all these things come in, say the challenge is 70,000 flows a second at 10:1 sample rates, and the T640 is just really bad. Multicast, all of this stuff needs to go in. Oh, multicast, yeah, it's great, isn't it? It works. A couple of talks, and people are talking about the internet and whatever else. I think one thing that I'm glad is that we work in an NREN environment. We are, we're not the internet, most of us here anyway. We have these dedicated networks that are not part of the public internet. They're generally private networks. And in a lot of cases, we do have multicast and have for a long time had multicast that works reasonably well, as long as you do all the bolting together. We do still have problems, though. The example on this one is just a little peak access grid, of course, uses multicast. So 5 megabits per second conference equates to a rather large peak in the CPU usage. This is a Cisco 7206 site access router. This is equivalent to 1 IPTV channel, but decent quality, decent bandwidth. So 400 people watching one channel on site is great. But when 5 people decide to watch 5 different channels at 5 megabits a second, we have a few problems. Well, they have a few problems. But these are sort of little funnies that start creeping in with multicast. That's all been sort of IP monitoring, IP and above. But it's we're pushing now into the optical areas. How are we going to do more advanced things at the lower levels? I mentioned the flow data. Well, people using the flow data for signature analysis, for incident detection, traffic type monitoring, packet headers only, sampled rates. There are limits to what you can do with it, but it is very useful. Our CERT guys they've been developing over the last few years, a guy called Torben Jandling, been working on a system that takes this bulk of flow data every hour, indexes it, looks at all the flows and pulls out. Well, it doesn't actually pull out what's bad. What it does is it says, no, these flows are okay. It's a TCP connection from there to there. It's on port 80, nothing special, throw it away. Ignore those. Ignores all the things that it thinks are safe, and everything that drops out at the bottom are the suspicious ones. And then they raise tickets, send emails to lots of people going like, you're spamming the network, you're scanning the network, you're doing this, that, and the other. There's a denial of service against this machine over here. It's coming from these places. Do you know about it? Can you fix it, please? We're hoping to integrate all that work into our new flow system, but that's just taking a little bit of time because they've done a lot of work on that. I'll talk about the optical splitting in a second. The optical network element data, the core of our network is managed by Verizon. So we don't operate the optical equipment itself. It's spread all over the country. There's 112 odd boxes spread across 100 odd sites. So Verizon operate it, but it's a dedicated network. So it's nobody else is using the equipment, and we can do what we want. Getting some of the data out in that sort of environment is slightly more challenging. But we have just managed to get everything in place now. So we're now receiving the SNMP traps from the equipment, and we can start pulling those in and using them especially for things like the LHC OPN, where we need to provide monitoring data through perf sonar to the end-to-end coordination unit and the ENOC. There are too many acronyms in this world. The Nortel boxes we have in one of our regional networks, which we also manage, are easier because the new software upgrade which just went in place means you can SNMP poll them. And we're hoping you can actually get some data through the SNMP as well. We can actually poll them. We're not sure what we're going to get out of it. But this is the telecoms world where TL1 has ruled forever. Now starting to see SNMP coming in there as well, which means it's much easier to integrate. I mentioned the packet capture. We're putting some kit in place at the moment. We have half of it, in effect. So these are the T640s that we run in the core of the network, and we have a bunch of fibers from them into the Sienna equipment that provide the core network. We are putting splitters in these fibers in line with them, and then running a glimmerglass optical switcher. So this is a box that you can control via a web interface, and you can basically select which of these fibers you want to come out of which of these monitoring ports. So if we buy a couple of NDACE cards and a box, we put them on the end, and we can select which of these fibers we want to monitor. So if we can afford enough NDACE boxes and cards and all the rest of it. Potentially we can monitor everything around the router, but there's about 16 fiber pairs going in and out, so it's quite a bunch of equipment, and they're not cheap cards. Being able to do this at 40 gig obviously would be an advantage, but I say they do it slightly differently in that they keep the 10 gig network monitoring cards, but you have a 40 gig to 10 gig times 4 splitter, which allows you to do these clever things. The 40 gig box does allow you to select which traffic you want to pull out though, so you don't have to take all of it in one box. What's it being used for? Anomaly detection, slight spelling mistake, nothing new. Packet signature analysis, encrypted signatures. One of the research projects has been taking encryption across the network and looking at things and actually finding that they can tell what traffic it is. They can't see what's in it, of course, but they can tell whether it's an encrypted web transfer, whether it's a voice over IP call, what sort of thing is going on in there, which is getting slightly scary, actually. So, what about sniffing packets? Interception. We have a bunch of rules which we gather are based on European law. And this is in the UK, it's the Regulation of Investigatory Powers Act. And later on, we have the Data Protection Act. The RIP Act covers when you're allowed to take things off a network. And what we've basically done is move things in line, as I'm sure you all know, with the telephone system. So whereas it used to be illegal to tap telephones and listen to somebody's conversation, it is now exactly as illegal to tap somebody's electronic communication in whatever way, shape or form it's taking place. There's no distinction in law between how it's being done. And this has had a big impact. The RIP Act defines two types of networks, public access and private networks. Janet is a private network, which means we do not provide public services. People don't come up to us, buy a service from us, and it can be anybody. Everybody who uses Janet is part of the education and academic community in some way, shape or form. Visitors to sites who are bona fide visitors are allowed in. But you have to be a visitor site. And this is fairly important for it. Because we're a private network, if there is a breach of the Act, it means that it's a civil case. It is about somebody proving that somebody else did wrong in a civil court, but it is not a police investigation, which makes it slightly different and gives some of our legal guys a slightly warmer, fuzzier feeling about doing some of this work. Breach by non-operation staff, anybody coming in just trying to hack the network, putting a sniffer in place, doing these things is still a criminal act because they're not the operator of the network. The operator of the network has the ability to do things to keep the network operational. You can do quite a lot of stuff on an operational basis. What you can't do is go fishing for things that may be happening. You can't just wake up one morning and think, oh, I think I'll look at all the packets flying across the network. Oh, look, they're looking at this website. They're looking at that website. Not really allowed to do that anymore. There's a link there which points to some stuff. And what we've basically had to do is put in policies in place that now researchers sign up to, which I think is on the next slide. So researchers come along, say they want access to data. How are we going to deal with it? I say, well, no access to data not required. I'm not sure what that first sentence was supposed to say. No access to data where not required, or something like that. So if you don't need something, you don't get it. So if for your research you're looking at packet size distribution, you don't need source and destination IP addresses. So it's easy. We just give you a whole list of packet size distribution, no problem. If you do need something that includes IP addresses, then is anonymization okay? Can we do it that way? You may get access to full data if you can really prove that you have to do it in that way, shape or form. And it's most likely that we would have to actually be involved in funding that because we think it's operationally important at that point. There's very clear areas. There are some areas which are no-go, and you just have to be careful. But researchers agree to a policy that they sign up to, which basically says, I'm going to do this research, this is how I'll disseminate it, this is what I'm allowed access to, and this is what I'm going to process. They're of course allowed to publish anything they want that they pull out of the data, but they're not allowed to publish their original data without agreement. I mean, if you're talking about packet size distribution, there's not so much of an issue. But in terms of access to data sets, it does mean that we can keep the data sets, we can hold them, and if somebody comes along to challenge what somebody's done, then they can have access to the same set of data and work that out. And so this works because Janet is a private network. There's a lot of things, if we were a public network, we would not be able to do in the same way, or we would have to directly fund because we think it's operationally important. Pulling all that stuff together takes a bit of effort. Database systems, we've got guys sitting at the moment coding all this stuff up into one or a number of large boxes. Some of the nice things that we're going to have in the system is that the measurement points are going to be able to, they're going to self-monitor, they're going to be able to load share between them. If it detects that one of them is getting too busy, it'll take measurements and move them onto other boxes. If one of the boxes dies for any reason, it'll take the measurements that box is supposed to be doing and shift them onto another box. And we can spread these around the network and measure whatever we want across them. So the key issue as far as we're concerned, the architecture is key to all of it. Providing the network that can do all these things, providing a monitoring system that is flexible enough to be able to take the data and extract it and deliver it to the users who want it is good. Stability and comparability of data, and the legal framework has become so important that we just cannot ignore it anymore. It's got to be done, and it's got to be done properly. Thank you very much.
So we have time for a few questions. I'll start off. I have a question.
You always get to go
I
first.
get to go first. That's the only benefit. So you talked a couple of times about limitations in router hardware that prevented you from keeping with your 1 to 10 sampling rate for NetFlow records. And I was curious about that because in the networks I'm familiar with, they typically start out at 100 to 1 sampling rate. And what is it you think you're going to lose if you went from, say, 10% to 1% sampling rate?
There are some papers on this, and it's an area of research at the moment. What level of sampling do you need in order to do certain types of work? Some of the papers suggest that around the 100 to 1 is the break point between being able to do security work and being able to track attacks versus not being able to do some of it. If you're doing sort of aggregated numbers in terms of how much bandwidth, how much of this type of protocol, that type of protocol, generally it's not a problem. Some of the work that our CERT guys are doing in terms of tracking incidents using flow data would become much harder at that lower sampling rate. So it's a good question. The jury's sort of still out at the moment, but when at the moment we're talking about 1,000 to 1 versus 10 to 1, which is a huge gap. If we can end up somewhere in the 100 to 200 area, I think that will be okay for most things, but we might lose 1 or 2 features that we do at the moment. But this is where the packet samples come in and do full rate. It'll be fine.
Anybody else? Questions? Okay, thanks.
Cool. Thank you.
And Steve Cotter from Internet2 is going to have a slightly different subject. He's going to talk about the new Internet2 network as he's being suited up here.
Okay, I'll put it in my pocket, yeah. Okay. Thank you, Steve. And thank you for coming to the session. As Steve mentioned, I'm with Internet2. For those of you not familiar with Internet2, it's an R&D network in the United States. Internet2 itself does much more than just have a network. We participate in a lot of R&D networking activities and support a lot of the community's efforts. But I'm just going to talk today about the network itself. In the past, we've had a 10 gigabit IP network that we call Abilene. This is the follow-on next generation network that we're building out currently to support the needs of the community. And the Internet2 community itself is a collaboration between R&E and industry. We've got over 300 members and participants on the network itself. And this is a network that we're putting together in order to support that. Let's see. Okay. Gonna give a quick overview of the network itself, starting with a high-level overview. A couple years ago, the community had put together a couple papers in collaboration with industry and researchers on what it is that the community was going to need with its next generation network. Our Abilene network was 10 gig leased wave network between our 11 core routers on a national footprint, and it provided IP services. The community looking forward said that we're going to need a lot more than just an IP service. We needed circuits. We needed kind of a dynamic capability. So in the last couple of years, what we've done is we've established a test bed called HOPI to kind of better understand the hybrid optical packet infrastructure requirements. And that effort's been led by Rick Summerhill, and helped us kind of determine what the architecture should be and how we can go forward with building this out. We also looked at some of the different networks that we're familiar with in the US and in the R&D community in the world. And Abilene was a leased wave network. We had another model to the other extreme, which was National Lambda Rail, which is a completely member-owned and operated. They own all the fiber, the equipment, and everything. And we took a different approach. What we did was we wanted to work with a carrier to kind of leverage the economies of scale, the efficiencies that we could get with them, and so that we didn't spend all of our time just running the network itself, so we could focus on supporting research and the collaborations within the community. So what we did is we entered into a relationship with Level 3 Communications, where they provide the layer 1 infrastructure on a dedicated system. By dedicated, I mean we have a separate fiber pair, separate optical gear. There are no other customers on this except for the Internet 2 community. But what they do is they fully manage it for us. They'll issue trouble tickets. They'll send their guys out to replace cards, and they manage the network to industry standard service level agreements. But the difference is that they are giving us total control of the infrastructure. We can provision as we want, where we want, when we want. So it's kind of a unique relationship, and we're in the very early stages, but it's working very well. Level 3 is running a separate instantiation of their network management software, and we get to control that. They're writing very close to finishing the software that will allow us to do the provisioning ourselves. Just we go in, point and click, we can see all the alarms, all the performance management, everything. So it was an approach that initially when we talked to the different carriers, they quite literally laughed at us when we said that we wanted them to run the network, but we wanted to control it. And they said, there's no way. We can't do that and still meet the service level agreements that you're saying that you have to have for a production class network. But we were convincing enough that we got Level 3 to do that, so that's the network that we built out. At Layer 2, what we're doing is we're deploying Sienna core directors using a control plane that's been developed as part of the NSF Dragon project to give us a dynamic capability across the network. And I'll talk briefly about that. And then if you're interested in learning more about that, I highly recommend you attend Rick Summerhill's talk tomorrow afternoon, where he'll go into more specific detail about the dynamic network and how it's built and working. At Layer 3, we're going to continue the same network that we had with Abilene. The one difference being that we're going down from 11 core routers down to 9. We felt we could do that because of some of the wave capabilities and the dynamic provisioning capabilities will take some of the traffic off the routed IP infrastructure. And we felt we could kind of look at getting a smaller IP network, number of routers, which has some advantages in cost savings and such. But these are the same Juniper T640s that we have in the Abilene network today, running dual stack v4, v6, multicast. Not much has changed there. We're just moving it over onto the different layer 1 infrastructure. We're also expanding the observatory, which is a data collection, co-location, and experimentation service that we provide for researchers. We're expanding it from just layer 3 down to collecting data on layer 1 and some of the layer 2 control plane work. And we're also integrating perf sonar for intra and inter-network performance analysis. So that's all being rolled out with the new observatory on the network. We also are extending the network for international connectivity, extending the layer 1 infrastructure out to the exchange points in Seattle, Chicago Starlight, as well as New York City at 32 Avenue City of the Americas, where a lot of international circuits come in. So we'll have a layer 1 capability out to there, as well as the layer 3 capability that we've had in the past. And we're also getting into, as Steve mentioned, some of the R&E networks in the US are looking at peering with the commodity internet. And so we were also extending into some of the peering points and at Seattle, the Palo Alto Internet Exchange, as well as Equinix Chicago, and we're looking at other sites that provide opportunities for direct peerings and peerings within the commodity services. Here is the layer 1 topology of the new network. It covers 13,600 miles worth of fiber. I believe that's around almost 22,000 kilometers. And it's set up in multiple rings across the US. And as you can see, there's lots of different colors on this map. The red sites, like here and here, are the city, the regional network that has a presence in that site, and the location. And you'll see that at each one of those sites there is a yellow dot. Those sites are what we call full optical add drops. All of the waves are going to be dropped at that site. The reason we're doing that, or able to do that, is that Level 3 is building out the Layer 1 infrastructure using optical gear from a company called Infinera. Infinera does OEO at nearly every site. So all the waves drop there, we get access to all those waves. And the idea being, if we're going to eventually evolve to a dynamic network, then we'll have access to all the waves in any direction at each site. So each of the yellow sites, like I said, will have a Sienna core director. They're running the Dragon control plane software. At each of these blue dots are sites, they're optical regeneration nodes, and we will have the ability to add or drop traffic there by the simple slotting of a card called a TAM. It's basically just a small GBIC, essentially. And that gives us the capability to drop traffic at any one of these sites. There's 56 of these sites around the country. So if it is more cost-effective to drop site, in between major optical nodes, we can do that. We don't have to backhaul someone all the way back to the core directors or the major routing sites in order to get them onto the network. The network build-out, we started this I believe it kicked off around October timeframe. And by our fall member meeting in December, we had 100 gigabits up between New York City down to Washington, D.C. to Chicago. And we were able to demonstrate with one of the regional networks called NextGen in New York, a live, uncompressed HD video feed as part of our plenary session to kind of kick off the network. And luckily, it went almost flawlessly, and it was our real first test of the network. And then we thought we'd press our luck, and immediately after the demonstration of the uncompressed HD video, we did a 100 gigabit interface demonstration. And we actually reprovisioned 100 gigabits along that path and tested it completely within 30 minutes of the demonstration. So we were quite pleased with how quickly we were able to provision that, and that was before we even rolled out the CNO core directors, which will actually do even more of the dynamic provisioning capabilities. So we continue with the build out up through Boston and back around through Cleveland. By March 2nd, we completed the build out down to Atlanta, and we continued to march our way across the country by April 19th. And a week later, we had it built out all the way to Denver. So this was going very quickly. Level 3 was able to turn these segments up incredibly fast. And as we were handed over to Layer 1 infrastructure, we had a team from our Network Operations Center at Indiana University following in behind them, doing the installations of the core directors and the observatory equipment and getting that rolled out. And just this last week, we reached the network up to Seattle and down to the San Francisco Sunnyvale area. And in just a couple of weeks, we will have that last segment handed over to us, and the build out of the Layer 1 infrastructure will be complete. So this is a very large network build that was actually done quite quickly, which is kind of a testament of the capabilities of Level 3, as well as the ease of management of the Infinera equipment. Take a more abstracted view of the network. This just has the sites that will have the CNO core directors, which will have the dynamic point-to-point capabilities between these sites. And again, this corresponds to where we have regional networks, and they have their presence in the Level 3 facilities already. Built on top of that, these are sites where we're going to have the routers located. As I said, we're going down from 11 core routers down to 9. We moved a couple of them around. There's no longer a router in Denver. We moved that to Salt Lake City. And basically we'll have an OC192 circuit in between each one of these routers, connecting them just as we have them built out in Abilene today. On top of this, we also have the Hopi test bed, and that's been in place for a couple years. It was on the National Lambda Rail infrastructure, had a single wave there. We've migrated this over onto this infrastructure, and it provides a test bed, as I said, for us to test some of the control plane work that we've been doing, as well as some of the new services. We plan to keep this going, in the future, to not only test out some of the things that we're working on, but also provide as a test bed for the community to do their own evaluations of different protocols and services. So, as I said, the community several years ago put together a couple papers to describe what sort of services and capabilities they wanted in the next generation network. And from that framework, we had as our objective to build out a flexible infrastructure, as flexible as we can make it, to do as many things as possible for the community. Again, we retained the best effort high-speed IP service, and we've expanded it from just a research traffic network to also peering with some of the content providers so that they can provide advanced content to members of the community. Keep in mind that we have everything from tier 1 LHC sites to little kindergarten classes connected to the Internet 2 network. So we have to meet a broad range of needs. With this network, we'll also be able to offer dedicated point-to-point wavelength services. We can do it either SONET or Ethernet. We'll be able to connect physically directly to either the Infinera equipment, directly into the level 3 owned Infineras at 10 gigabit, either OC192 or 10 gig E. If you want a sub-wavelength circuit, you can connect at 1 gig E to the core directors and just get a dedicated static wavelength, as a lot of people use today. But the new service that we've been developing is to complement the existing services that we have, and that is to provide a dynamic circuit service. And this can be either a point-to-point Ethernet VLAN circuit framed over SONET, as well as just a regular point-to-point SONET, which we can provision in increments of 50 megabits, the STS1 level. And we're going to have the regionals connected to the core directors using a 10 gig interface, and to be able to split that traffic out and send it in any direction in any increment of 50 megabits. So for example, the University of Texas connects in Houston as their main point of connection to our network. They could send 3 megabits to New York to send it over here. They could also, through that same interface, send 1 gigabit to Starlight for some collaboration in Asia, and send 100 megabit stream for a video conference to another researcher on UCLA campus. So we'll have that capability. These dynamic services are new. Obviously, we're trying to not only put these together, but learn as we go. This is something that not many people are doing these days. And so we're trying to figure as we go along. But ideally, what we're trying to do is to provide to researchers a circuit-like service that provides guaranteed bandwidth and predictable latency between any two endpoints. And the challenge is going to be to get these not just across the backbone, but down to the campus level. Last mile is always an issue. We recognize that. We've put together some workshops that we're taking around the country to the different regionals to explain how this works, get some hands-on experience with this. It doesn't require a whole lot. Some very inexpensive servers to go into the regional networks and act as a network-aware resource broker, or kind of extend the control plane down into the regionals. But we're obviously having to work with the regionals and helping to educate them on what's needed and how it should be rolled out and how they can take advantage of these capabilities. We see some of the researchers using this for a way to implement specific policy or traffic engineering requirements. And one of the benefits that we see is what I identify here is router bypass, ability to express links between endpoints. We have a very large country. It takes a lot of resources to get a circuit, even if it's just IP traffic, from, say, New York to Los Angeles. If you don't have to run it through a bunch of expensive router interfaces along the way, and you can bypass them with this infrastructure, then that's something that we are looking at doing in order to get some cost efficiency in the backbone. So we think these Dynamic services will enable rapid provisioning, but also allow us to kind of be more efficient in the utilization of the capital investment that we've had to make in this large national network. You know, as you guys know, it's not a trivial task to get circuits built across multiple domains, multiple networks. So, you know, it takes a long time. There's errors. If we can automate this as much as possible, then we feel that we've accomplished something that can be useful to the community. And we still have a lot of work to do with as far as automated reservation, allocation of the network resources, but that's something that's an ongoing work, and we'll be continuing to roll that out as the service matures and we continue to develop it over time. Here's a kind of again, an abstracted view of how this would work. The user can make a request either through a GUI or application-specific topology request into an XML request. It goes into the network, and we are able to do this across multiple services, whether it's TDM, Ethernet, or across the IP network using MPLS or layer 2 VPNs, and do it across multiple domains, multiple layers, and across multiple vendor equipment. So, you know, we would set that up either, like I said, the request goes in, if it's to go to across the regional network, across our network, to the GEONT, that can be set up, as well as setting it across a regional network that may be running just a 10 gig Ethernet service, as well as a routed infrastructure like ESNet has. ESNet's the Department of Energy's network. They are actually partnering with us on this network build-out. Because there's a lot of close collaboration between researchers on the campuses and the Department of Energy labs around the country, it made a lot of sense for us to work together and help kind of reduce the overall cost to the community in providing this sort of infrastructure. So we've built out our co-location facilities with ESNet in the same suites, so we don't have to pay for cross connects. They are using waves on our network, either for their point-to-point wavelengths, or they're also using a wavelength for their IP infrastructure. They're kept separate, but we will facilitate the collaboration between the work that the high energy physicists are going to be doing with the work being done on the campuses. So some of the applications that we see using these dynamic service capabilities, obviously there's going to be some that we haven't even thought of yet, but these are just a few of what we've been talking about as possibilities for this service to kind of provide this connectivity between collaboration sites. You've seen a presentation yesterday on the radio astronomy, the EVLBI network, and I'll show an example of that. We see these circuit services really carrying high bandwidth, limited duration flows, and so we think that could be a use of the network. Obviously, it will still continue to use the IP network for generic internet access and use, but like I said, there are things that people aren't even thinking about. Security guys are very interested in this because they think if they get hit with a denial of service attack, it'd be nice to be able to, on demand bring up a second connection to the router and keep the site alive while still being able to analyze the attack. So it's something we didn't think of, but it's something that could definitely use it. So again, here's an example real quick. I'll go through this. The EVLBI example with your remote storage clusters. So you have the traffic flowing. It could be dynamically set up, could be statically set up between the telescopes and the storage clusters. But then we'd have the capability to set up these dynamic waves to the correlator and then also build them across the network to the analysis station, and it could work, in that manner. This is my last slide. Talk about some of the collaborations that we're doing specific to, our friends here in Europe. There's a group called the DICE group, stands for Dante, Internet 2, Canary, and ESNet. We've been working very closely with them on interfacing some of the work that ESNet has done with their Oscars program with HOPI and integrating some of the AAA work that's been done. We've also been working with folks on we'll call it kind of a stitching project to describe the data layer interconnections and how those are going to be met so that we can build these point-to-point paths across multiple domains. We've also been having talks with the folks at Phosphorus and SurfNet and several others, and coordinating with the various different groups and standards bodies. So we still have a lot of work to do. The layer 1 infrastructure is nearly complete, and we're in the process of moving folks off of our old network onto the new infrastructure, and then we'll go from the build out phase now into the management of the network phase. And so we're looking forward to that, very excited about the potential that the network has, and it's going to keep us busy for quite a while. So thank you. If you're interested in any information about the network, the first two links are very good. The second one, the blogspot.com, is the network engineers from the Indiana NOC have been keeping almost daily reports on how the build-out's gone. It's very interesting to see some of the issues that they've run into and how they've overcome those things that have popped up. So if you're interested, I'd definitely check that out. So thank you.
So I'm not allowed to ask Steve a question because I work for Internet 2. So questions?
As I got it first, I'll go first. What experience do you have about setting up the routing automatically at the end sites? It's fairly straightforward to set up the light path,
Right.
but when you connect into the end site and you make an internet loop, that can be quite embarrassing.
Yes, and I don't think we've really gone there yet. We're still working on this. Rick, I don't know if you've had some discussions about that, haven't you? There's a project that you guys are involved in.
Project to look at how to set up if you're creating a light path from router to router. Currently, we've just been focusing on light paths to host to host, or switch to switch.
Right.
So you never talked about the infrastructure from the point of view of the merger with NLR.
Okay.
So will there be an infrastructure merger, or is it just you're going to have a common CEO and that's it?
That's actually part of the ongoing discussions right now. Is how do you merge them? What capabilities do you want to keep? Do you keep them both? Do you keep one? Those are part of the ongoing discussions, and nothing's been decided at this point. So it's probably too early on to say, what may result from the merger, at this time. But I think there's some pretty, obvious things. NLR has a very valuable fiber network that will probably be retained by the community. But a lot of the other things are still being worked out. Yes, sir.
Okay, this is not a real question, it's more a comment. You had the idea of express paths, bypassing some of the routers and so on. And you gave you a few of the advantages. But there is still another advantage. That is, if you want to do mathematical calculations, network calculus, on your network to get the guaranteed worst case situation, the number of routing hops is really disastrous. So therefore, bypassing them is definitely an advantage even in that case.
Mm-hmm.
Thank you.
Yeah, that's a good point. Thank you. That's it.
Let's thank our speakers again for one more reminder as the thing proceeds, your evaluation forms. Don't wait till the very end. As speakers and